Chapter 9 deals with the differential analysis of fluid flow. So you have a differential equation for the conservation of mass, and you have a differential equation for linear momentum. Now, it's not a conservation of linear momentum, it's a linear momentum balance equation. It's basically F equals ma. And we're going to get to what we call the Navier-Stokes equations. This is the bottom line for this. It's usually the jumping off point for computational fluid mechanics. So you're going to solve for all these vector and scalar fields that are relevant to fluid flow. You're going to find the pressure everywhere in the domain and the velocity everywhere in the domain, or at least at your nodes of interest in your finite element or finite difference gridding up of your domain, computational fluid dynamics. And this is a good bottom line for the conservation of mass. There it is. There's an equation. It's called the continuity equation. This is the pinnacle or the result of this chapter, differential analysis of fluid flow. And then this looks like F equal ma. Maybe it doesn't look quite like F equal ma. Maybe it looks like ma is equal to F. Okay, but let's take a look at this. This is called the Navier-Stokes equation. This one right here. It's the momentum equation. Let's take a look at the first equation, the continuity equation. What do we see? What is rho? Property, mass density. It could be represented as a scalar field, meaning density varies throughout my domain, but often density is constant. So often rho is equal to a constant. But in general, in this equation, it could be a function of time, it could be a function of x, y, and z, thinking about 3 Cartesian coordinates. So it's in general can be a scalar field. Then what do we have here? We have v. What is v? Velocity field. So it's the velocity represented as a vector at every point and at every time. So that's our velocity field. So we can take the scalar density and multiply by v. You still have just another vector field. But what is this? We have a del dot. Ooh, that's mathematical shorthand notation for the dot product. That's what that dot stands in for. So del dot, that del dot often called the, good try, keep going. He's close to the curl. In between the curl and the gradient is the divergence. It's the divergence. And so you take the divergence. So, ooh, we have all that mathematics that we had in EA2, Engineering Analysis 2. We had the vector, differential, and integral calculus. We were introduced to divergence, gradient, curl, things like that. So this is only a scalar equation. When you're all done with it, it's just one equation. This one down here is a vector equation. So we could do the x direction, the y direction, the z direction. It basically busts into 3 scalar equations, the vector equation does. Because just like, remember in statics you had the sum of the forces equal to 0? That's a vector equation, but you bust it into sum of the forces in x, sum of the forces in the y, sum of the forces in the z, so 3 scalar equations. So let's take a look at down here. I see mu. What's this? Viscosity. That's a property of fluid. Often you could write it as a function of time, function of x, y, and z. But often it's just a constant, just like density is a constant. All right. But it's a material property that could depend on location, and temperature could change by location. Hence, it would change by location as well. Well, how about the next maybe easiest term? What do you think that is? G. Gravity, gravitational acceleration, or force per unit mass. That's what gravity is, a weight per unit mass. That's that ratio. It's in a vector form. So we have typically a coordinate system. Maybe it's x, y, and z, and they show g maybe is a vector coming in this direction, and so g would be 0 in the x, 0 in the y, and minus the magnitude of 9.81 meters per second squared, lowercase g without any arrow on it, no vector notation, just our standard scalar g in the z. True? So that's a vector representation of the gravitational force per unit what? Mass. True? Isn't that what g is? Yeah. Okay, what is P? Pressure. Is it a scalar field? So we could talk about the pressure at any time and location in the domain of interest. And then what's happening to P? We have something operating on P. What is that? The gradient. Del P. Gradient of P. So we have the gradient operating on P. Okay. So this tells it how it's being pushed. This tells it how it's being pulled. Those are like forces acting on it. Right? This Navier-Stokes equation is F equal ma. And so the forces and forces. This is a body. This is a surface force. You can think about a particle of fluid and it's being pushed by the other adjacent particles of fluid. All right. Well, this one. Well, it's got the viscosity in it. True. It's probably due to a surface force, but not by pushing, by sliding adjacent surfaces, sliding. So through viscosity, if the chunk of fluid's here and it's fast on this side and slow on this side, then it'll feel a viscous shear stress on the chunk of fluid, right? And maybe not so large a viscous shear stress on the chunk of fluid. Okay. So I know it's embedded in some mathematics, but what is so it's operating on V, but what's operating on V? What is this notation? It's del squared, right? So what's another name for del squared? Laplacian? So this is del squared or Laplacian, which is del dot del. That's another way of writing it. Del dot del. So you take the gradient, well, the divergence of the gradient. Let's look over here with this mass. Oh, that's mass per unit volume. Isn't it density? And then what is this? That looks like some acceleration. What is this? Is that a typo, a big D there? I don't understand that big D. Material derivative. And so that's pulling in the concepts of what we taught when we did kinematics. So this is the material derivative of the velocity vector field. Here, let's do this, because this really was a telling you what the bottom line is in the equation, trying to then jog your memory about it, a lot of the mathematical background. So what about that dot product? Remember about dot product, if you just had a vector A dotted with a vector B, what is it? Well, the vector A can be a sub xi plus a sub yj plus a sub zk dotted with the vector b sub xi plus b sub yj plus b sub zk. That's some notation like that. Different textbooks, different authors have different notation, but I think you grasped that, true? And so when you have the dot product of this vector A, it's just going to be the x component times the x component of A and B added to the multiplication of the y component and the y component of A and B added to this. True? Look good? Now if somebody says gradient, well, what is that? Sometimes they put a vector over it. Most of the time I leave it off. That's just me. Okay? Some people emphasize they put a vector over it because this could be written as the partial with respect to x in the I, the partial with respect to y in the j, and the partial with respect to z in the k. So it's like a vector. It's just waiting to operate on something. It wants something to differentiate. Give me something to differentiate with respect to the x and the y and the z. All right? So how about now if I say divergence, del dot? That's how we would write it. Or maybe I should back up here. Give me a simple vector field. Not a vector field, scalar field. Give me a simple scalar field. Let's say P is equal to 2 times x times y. Would that be a simple two-dimensional? I don't even have z in there. I don't have, it's just 2D, x and y. So could I take, and can you take, and get the gradient of that P may be representing pressure, scalar field? Well, sure, you could do this. This is what I wrote, P is equal to, you take the derivative of that P with respect to x in the I, the derivative of P with respect to y in the j, and the derivative of that P with respect to z in the k. And so let's do that derivative with respect to x. You get 2y. Do the derivative of P with respect to y. You get 2x. And the derivative of that P with respect to z, 0. And you've just successfully done the gradient of a scalar field P. True? Okay, good. Now we'll get to the divergence, del dot. And del dot is just like this dot right here. And instead of A, put del there for A. And it would operate on some vector field. Let's just have it operate on V, where V is equal to Ui plus Vj plus Wk. Does that make sense? That's our standard notation for our velocity vector field, UVW. The x component, the y component, and the z component. So when we take the divergence of V, that's equal to the partial with respect to x of u added the partial of v with respect to y added the partial of w with respect to z. True? Thumbs up? Look good? And then curl, we're not going to deal with it, but you would take del cross. All right? I don't want to deal with it right now. It's linear momentum in this chapter, not angular momentum. If we did angular momentum in this chapter, we would do cross. True? And then the Laplacian. Oh, what was Laplacian? Del squared. That's del dot del. And so if you work through it, it's the second derivative with respect to x of whatever you're going to feed it, the second derivative with respect to y of whatever you're going to feed it, because it's an operator, just like gradient's an operator, divergence an operator, Laplacian's an operator. It's what you have it operate on, right? And so if we look back, what did we have? We had del squared operating on something. Well, you had it operating actually on a vector. And so you would do it for the u component, you do it for the v component, and then the w component of the vector. Can you do this? Can you write an equation for a two-dimensional scalar field? Pick something. Say it's temperature. Say it's pressure. Say it's density. Say it's viscosity. Those are all good scalar fields. Can you just make one up? Why don't you do that right now? I'm going to go ahead and pause. So who has a scalar field they made up? You got one? Give it to me. What's it? 2xy plus 3z. Is that going to be for t? Sure, let it be for t. Doesn't matter what t is. Can you take the gradient of that scalar field? You could. Could you take the divergence of that scalar field? This is where it's applying to your memory. No, you need a vector field to take the divergence of it. It doesn't work. Doesn't work, okay? What about if you wrote a two-dimensional vector field? Maybe call it V for velocity. Something in the I, something in the J. You just add them together, whatever it is. So you have to make up some function of x and y. You could make up z too, but I said 2D. That's right? So if it's 2D, maybe we throw out the z up here, get rid of that, and we're back to 2D. So you see what we're doing? Just making you be creative. And so v would be something like, I don't know, anybody want to give me a function? It's your chance to be creative. I'm begging you to be creative. Pardon? 3x squared. And somebody else for the y component, the v component, you know, uv. Throw one out. What? Half? Half times what? Y. There you go. Simple. You don't want to go too hard. Now, can you take the gradient of that vector field? Well, you could take the gradient of each component of it, but really the gradient acts on a scalar. Could you take the divergence? Yes. A strong yes. And yes on the curl as well. But we don't have time for the curl today. So calculate now. I want you to do this. I'm going to walk around and see if you can do it. Can you calculate the gradient of that pressure field? And it's in 3D. It's 3D. And then can you also calculate the Laplacian of this pressure field? And yes, that's 3D as well. So I'm going to go ahead and pause and see how you do. All right, so a lot of you were able to do it on the gradient of the pressure is equal to the partial of the pressure with respect to xi plus the partial of the pressure with respect to yj plus the partial of the pressure with respect to zk. That's equal to 2yz squared I plus 2xz squared j plus 4xyz k. And some people put an arrow up there or not, doesn't matter to me. And there you go. Now for the Laplacian, it's del dot gradient of p. That's the Laplacian. Sometimes it's written del squared p. But what's del squared? Del dot del. All right. So you already have this as the gradient to p. So I have to take the divergence of that, which is, this is a dot product. It's just the partial with respect to x of 2yz squared added to the partial with respect to y of 2xz squared plus the partial with respect to z 4xyz. And a lot of people were able to say 0. But then some people wanted to put an I there. Should it be 0 without an I or a j or a k? And then a 0 without an I or a j or a k? And then it's equal to 4xy. So the Laplacian of that pressure field is just 4 times x times y. Oh, it varies as you move around in different locations, x and y and z. And its magnitude is equal to 4 times x times y. True? So Laplacian operator, if you feed it a scalar, you get back a scalar field. And the gradient operator, if you feed it a scalar field like you should, what do you get back? A vector field. A vector field. Okay. It's very interesting, Wolfram alpha. You can just go and say, take the gradient of, and then just type it in, gradient of. Maybe I shouldn't show that to you, right? People will be out on Google in the middle of an exam on their iPhone. Oh, he wants me to take the gradient of this. Fine, I'll get it done. And then even Laplacian of. And guess what it comes back with? And guess what it comes back with, this notation? It's a curly bracket, something, comma, something, comma, something, curly bracket for a vector. Okay, and there you go. Calculate the divergence of this velocity vector field. So I have to calculate del dot that v, which means that I take the partial with respect to x times z, maybe I should leave more room, z times b minus constant cx squared plus the partial with respect to y of 2cy plus 2xy plus the partial with respect to z of 3axz plus bxy. Is that true? Is that how I take the divergence of that vector field? Thumbs up if you agree. And now you just recall how to differentiate. So this one's a little tough. We're going to have z times b minus cx to the 1, and then we'll have minus c. Did I do that one right? And then this one is going to be 2c plus 2x. And the next one is going to be 3ax plus 0. 3ax plus 0. Look good? Done. Right? We're not going to get anywhere on these Navier-Stokes equations unless we're able to understand the notation. And there's del's, and there's del dots, and there's del squareds, and there's pressures, and there's velocities, right? And they all mean something. Calculate the gradient of P in, monkey wrench here, cylindrical coordinates. And let's take a look. Did they give me P in cylindrical coordinates instead of being x, y, and z, which are Cartesian? Isn't it r, theta, and z in cylindrical coordinates? Isn't that it? R, theta, z? And so I have to recall, okay, the gradient of something in cylindrical coordinates. What I do is I take the partial with respect to r, e sub r. What do you mean e sub r? A little unit vector in the plus r direction, true? And then probably the derivative of something with respect to theta, e sub theta. I'm trying to remember this. I'm from memory, right? And then something derivative with respect to z, e sub z, right? You see what I'm doing? It's I feed it something. The same something goes 3 places over here on the right side. But there's a error. I don't quite have the right side correct. And how do I fix the right side? Can you see it? Do you remember how to do the gradient in cylindrical coordinates? Professor, that's why we spent a lot of money on textbooks. It's in the back of the book, in appendix, or in the cover somewhere. But does somebody know how to fix this equation? Let's narrow it down. There's a problem with this term, a problem with this term, or a problem with that term. You all have to vote A, B, or C. You have a 33% chance randomly getting the right answer. Are we ready to vote? Everybody's going to raise their hand when they get the vote. A. Nobody, not one. Oh, one person says there's a problem with A. All right, you're brave soul. B. Well, you can't vote again. No, you want a 66% chance now. If you're voting twice, you can only vote for one candidate. Oh, you do? Really? Okay. Okay. There's only a problem with one of them. All right. You'll go back to A. She's back to A. All right. Now for B, 1, 2, 3, 4, 5, 6, 7, 8. Okay, for C, 1, 2, 3, 4, 5, 6. Let me ask you this. Does the equation have to be dimensionally homogeneous? Does each term that I want to add, does that have to be of the same dimensions? Okay, so whatever is coming in here has the same dimension, and that's going to contribute the same to each of the three terms. But what about this R? What do you think it is, R? Length? So by the derivative, I'm having 1 over R, 1 over length. What about the Z over here, Z? Length. What about theta? Angle, not length. It's dimensionless. Theta is dimensionless. So how would I fix it? Put a 1 over length somewhere. And put a 1 over R. And there you go. That's fixed. Now, yeah, I can take that function and shove it in right here. And in the interest of time and trying not to rewrite everything, this the gradient of that pressure field in cylindrical coordinates comes back with something. Can you see what it is? Take that derivative of that with respect to R. What do you get? 2z e sub r, and then 1 over r times the derivative with respect to theta, 0 e sub theta. So all that's just 0, plus the derivative with respect to z, 2r plus 6z e sub z. There it is. I mean, I can clean that up, get rid of that because it's 0, but that's clean enough. True? Who's heard of Divergence Theorem? Yeah, everybody has. It's one of those. It's not the Stokes theorem, it's the Divergence Theorem. Sometimes people say Gauss's Divergence Theorem, but probably you don't need to put Gauss there, right? It's just the Divergence Theorem. So what does it mean? We use it all the time. And often we have area integrals. We have an integral over an area, dA. And we want to convert that area integral into a volume integral. That's it. That's Gauss's divergence theorem. If I have a surface integral over the complete surface enclosing a volume, not a partial surface integral, over the entire area completely, then I can convert it into a volume integral. Now, what is it? Usually the surface has a unit outward directed normal vector, and we dot product something. Let's say V. V is in fluid mechanics, velocity field. So you get the velocity vector at every point along the surface. You dot product it with the outward directed unit normal vector. You sum it up, make the integral over the entire surface. And if you're looking to make this integral, you can now replace it via Gauss's divergence theorem by a volume integral of, guess what? The divergence of V over the volume. That's it. That's Gauss's divergence theorem. This is the way it's written. I think I wrote it this way. So you have the integral with the circle through it. What's that mean? Closed surface area integral. You have some generic G. G for generic. Okay? V I use for velocity, but G generic vector field. What is this N? Unit normal vector outward directed, perpendicular to my surface. It changes as I move along the surface area. Is that a dot product, just like the dot products we studied? Yeah. And so we're saying, do this integral over the area. Often, this is what we start with. This is we transform it into a volume integral. And the volume integral is a lot easier. We take the divergence of G, and then we do the volume integral with respect to it. Compute the surface integral of this integral, integral V dot n dA, where V is three-dimensional velocity in Cartesian coordinates. It's 3xi 6yj, 7xyk. And you want to compute that over the area, where the area is defined as the area of a sphere of radius 2 centered at the origin. That's a tough problem. A sphere of radius 2 centered at the origin. That means the location of the surface is x squared plus y squared plus z squared is equal to 2 squared. All those combination of x, y, z locations that satisfy that requirement, that equation. Isn't that describing the surface of a sphere? This is so nasty, we employed the something divergence theorem. Gauss's divergence theorem, we just call it the divergence theorem. We want to employ that theorem, okay? How do we do it? We'd say instead of doing that over the entire surface, we'll do the divergence of V over the volume, over the entire volume enclosed. Okay, calculate the divergence of that vector field. If given this V, del dot V is equal to three plus 6 plus 0. Oh, this is lovely. It's a constant 10. See that? Oops, 9. I can add. It's a good day. Thank you. That was a test to see if you're awake. No, that was my slip and fall. So now I have the integral of 9 dV. I pull that outside. And so my answer is just 9 times the volume of the sphere of radius 2. Oh boy, I can't remember the volume of a sphere. Is that 4 pi r squared or 4/3 pi r cubed? I can't remember. Which one is it? Second one, and you can tell by the units. You need length cubed. You need r cubed. Is this correct for the surface area of the sphere? 4 pi, at least I remembered something, right? But 4/3, so you multiply down here by 4/3 pi r, in this case is, the radius is 2 cubed. And there's your answer. So this very nasty integral, almost impossible to do analytically, by using Gauss's divergence theorem, is easy to do. Make sense? Compute another one over the surface of a cube, going from 0 to 1, 0 to 1, 0 to 1. Well, it's the same thing. I wouldn't want to do that by actually slugging it out, doing a surface integral over the 6 faces of my cube. Maybe I'll take and use the divergence theorem, compute the divergence of V, and find out what that is. So let me do this. Let me pause and let you compute the divergence of this vector field, and then see if you agree with me, okay? So you do that right away, and then compute the integral over the surface of a cube. All right, so it was good to see that a lot of people were getting 4xyz for the derivative with respect to x here, and then they were getting 16xyz for the derivative with respect to y on the j component, and then minus 10xyz, so it's summed up to be 10xyz. 20 minus 10, 10. All right, then we are going to go ahead and do the integration of 10xyz over the volume dv. And the dv is a dx running from 0 to 1, and a dy running from 0 to 1, and a dz running from 0 to 1. True for our cube? And so the answer is going to be, well, I get 10 divided by 2 x squared, and the y and the z go along for the ride for the first integral, and then integral 0 to 1, 0 to 1, dy dz. Then I bring it up here, and the integrand becomes 5 yz. Then I integral 0 to 1 dy, integral 0 to 1 dz. Okay, then it's 5 halves y squared z. Y goes from 0 to 1. Then the integral 0 to 1 dz. Okay, so now it's 5 halves z integrated between 0 and 1. I didn't leave enough room, so I'll just have to throw it up here. It's 5 fourths z squared 0 to 1. So the answer finally becomes 5 fourths. Did I do that okay? Look good? Yeah. True. Great exercise in integration. I see no fluid mechanics in it, but hey, good math. Now there is consider this. You have the mass of a sphere of radius 3 meters. So that's the radius of my sphere. It's centered at the origin. It goes out 3 meters. Given the mass density, rho is equal to a constant A plus B r squared, where A is 900 and B is 10 and r squared. So that's my analytic expression for mass density. And notice that A has units and B has units. Kilogram meters to the fifth. Good. R is the radial distance from the origin in meters. Okay, so calculate the mass of that sphere. How would I calculate the mass of the sphere? I would sum up little chunks of the mass over all of the sphere. The little chunk of mass is the mass density times a little chunk of volume. And I probably want to work in spherical coordinate systems. And so what's my little, I'm going to do a one-dimensional integral with respect to r going from 0 to cap r. I just have to remember the right to get the little dv for every little dr. And what is that? I paused to embarrass you, right? I embarrassed myself, so I get to embarrass you. No. What is it? How about this? It's the area of the sphere at location R. Because if I have the area of the sphere at location R, and then I bump it out a little dr, isn't that a volume? True? So what's my area of a sphere at location R? 4 pi r squared. 4 pi r squared. What do you think? So is that what I put right in here? So I just put 4 pi r squared dr, and then I integrate from 0 to cap r, where cap r is equal to 3. Is this going to work? And so I shove in for the density this function, 900 plus 10 times r squared. So you do that integral, okay? So the integral that needs to be done is 0 to 3, 900 plus 10 r squared times 4 pi r squared dr. You know I don't like to do those integrals like that, do you? But if I had to do it, how would I do it? I would do it with a little help, right? And so, can you see I just typed in integrate 900 plus 10 times r squared times 4 pi r squared from 0 to 3. It said, I don't know exactly what I think, but I think you want me to do the definite integral 0 to 3 of, and then it just, I look at it. Yeah, that's what I want. It's around 107,000 or 108,000. So there's your answer. Okay. Somebody says, I'm an engineer. I really don't want to do integrals like this. I go back to this problem and I say, why don't I just take rho average times the volume of a sphere of radius 3, which is 4/3 pi r cubed. That's the volume. What's the average? Well, let's see. When r is equal to 0, rho is equal to 900. When r is equal to 3, rho is equal to, can you see what it is? Put 3 in there. 3 squared is 9. 90. 990. How about if I just multiply that by 945? Guess what? It's going to be really close. It'll be pretty close, okay? So don't lose sight of how to do things quick on the back of the envelope. But this is the way to do it mathematically, analytically. Okay, because why did I want to do that? Because I want to derive the continuity equation. And I want to derive it with terms you can understand. Okay, so basically you start with the Reynolds transport theorem, and it looked like this. It said the time derivative of the mass in the control volume is equal to the negative of the outgoing mass flow from the surface, across the surface of that control volume, calculated by integral v dot n times rho dA. Does that? So this is the outflow. That's why it has a negative sign on it, because it's removing it. And so if that integral is positive, the amount of mass in the control volume is going down with time. So you need that integral. How would I calculate the mass in the control volume? Well, do an integral, just like the one we just did. Integral rho dV, but instead of being for a sphere, it's a general volume. So I also bring it this negative sign, I bring it to the other side of the equation, so everything's equal to 0. Then what do? I apply the divergence theorem on the second term, so I can turn it into a volume integral. And I take the time derivative inside the integral. Now it turns from an ordinary derivative to a partial derivative. Why? Because this integral of rho dV should have gotten rid of x, y, and z, and it should only have been at the maximum of function of time. Does the mass in the control volume go up or down with time? But then when I bring it inside the integral, I have to have a partial derivative because rho inside can be a function of x, y, and z, not just t. Make sense? But now I have a volume integral, combine them. So everything, this square bracket is what we call the integrand of that volume integral. That volume integral was arbitrary to begin with, any region of space in my fluid flow field. And because it's arbitrary, at every point then it has to be equal to 0. There's a little logic in that. Okay? If I have a region of space and the fluid flow is going through it, and I do it for that volume, I do it for that volume, I can do it for that volume, I can do it for this volume, I can do it for that volume, I can do it all the way down to a point. So at every point, that integrand has to be equal to 0 for it to always be equal to 0. And that is our continuity equation. How do you like that? So you can write out the continuity equation in Cartesian coordinates in its grand and glorious form. Partial of rho with respect to time. Oh, I just have to express the divergence on operating here. Would that be the partial with respect to x of rho u plus the partial with respect to y of rho v plus the partial with respect to z rho w? Is that what it is? Yeah. And is this a scalar equation? The continuity equation is a scalar equation. If you want to, you can also expand it in cylindrical coordinates. Running out of time, so I digress, let you do it. Incompressible. What do you mean? So a lot of times rho is equal to a constant. If rho is equal to a constant, I think this continuity equation can be simplified. So what about that time derivative? You know, the partial of rho with respect to time. Does that go to 0 if it's rho is a constant? Yes. And then can I take that row outside the integral or the divergence operator, if it's constant, and put it out here? And it's like this. If a times a function of x is equal to 0, does that mean that function of x has to be 0? Because a is not 0. Our mass density is not 0. We just said it was a constant. So you end up with del dot v is equal to 0. That's our continuity equation. It looks almost too simple to be useful, but it is. That's our continuity equation for incompressible substance. You can also derive the continuity equation starting with little control volume that's infinitesimally small and shrink it down. You get derivatives. It's in the textbook, and I just don't have a lot of time, so I'm going to skip it, okay? Stream function. Well, our continuity for incompressible equation is the partial of u with respect to x plus the partial of v with respect to y. That's equal to 0. See, that's what it boils down to. It's also, I forgot to mention, it's two-dimensional, Cartesian, 2D Cartesian incompressible. And so del dot v equal to that. Well, they noticed a long time ago that if you could find u, if you could find a function psi, which is called the stream function psi, such that the partial of psi with respect to y is equal to u, and v is equal to negative the partial of psi with respect to x, then it guarantees satisfaction of the continuity equation. Just stick u in here and v in there, and what you find is that the second derivative of x, y, of this stream function minus, that's why the minus sign's right there, the second derivative of the stream function is always going to be 0. And so they made the observation, oh, we look for a stream function that describes our two-dimensional, incompressible, steady flow field. Let's solve a problem. Consider a fully developed flow between two infinite parallel plates. This is the top plate. This is the bottom plate. And in between is the fluid. It's separated by a distance h. And the top plate moving at speed v. And the bottom plate is not moving. V down here is 0. The flow is steady, incompressible, and two-dimensional in the xy plane. The velocity field is given by, and here it is, it's just all in the x, nothing in the y, and it's a linear profile, and if you plot it, that's what it looks like. So u is a function of y, and if you put in y equal to 0, you get the bottom no speed and no velocity. If you put in y equal to h, you get cap v back. So this is a great function for u as a function of y. Generate an expression for the stream function psi along the vertical dashed line in the figure. Here's the line right there. For convenience, let psi equal to 0 along the bottom wall. So they're saying down here, psi is equal to 0. Well, we go to our continuity equation. We have the partial of u with respect to x plus the partial of v with respect to y is equal to 0. True? We said that u is the partial of psi with respect to x, and v is equal to minus the partial of psi with respect to y. In this case, what is u? U is, that's like I'm working two problems at once. What is u? It's going to be cap v y over h is equal to the derivative of psi with respect to x. It's like an ODE, it's a PDE because it's a partial derivative. So we separate, integrate, and we find that psi is equal to V y divided by H. I messed up. This is the derivative with respect to y. I'm sorry. This was the derivative with respect to x. True? How many people saw that? Yeah, keep me honest now. So now, what do we pick up? We pick up 1/2 y squared plus any function of x, because if I just take any function of x and differentiate it with respect to y, this will be satisfied right here. Okay, let's work over here. What is v for this problem? 0. So we have minus the derivative of psi with respect to x must be equal to 0. So psi is equal to any function of y. So now I look at both of these and reconcile them. And what we find is that the stream function is equal to 1/2 y squared cap b divided by h. And you can have a constant, just any constant is like a function of x and a function of y, a constant. But when you come in and say put psi equal to 0, that constant is equal to 0. So psi at y equal to 0 is equal to 0. That constant goes away, and so there's our stream function. So that is our expression for the stream function right here. What is the value of the stream function psi at the top wall? Well, psi at y equal to h is equal to, we're going to have 1/2 cap v h squared divided by h. So we'll get rid of one of those h's, and there you go. Okay. All right. You can also work out what is the volumetric flow rate. It's not asked, but part C. The volumetric flow rate going down in between the top plate and the bottom plate. Isn't fluid crossing this dashed line every second? What's that volumetric flow rate equal to? Well, that volumetric flow rate AV, just by looking at it, it's a linear velocity profile, would be 1/2 v y over h times h, and it's per unit depth. So that's the volumetric flow rate per unit depth. Agree? That makes sense? Good. Now what you can do is I'm going to need a little more room here, is you can say I can integrate u with respect to y from y equal to 0 to h, and won't that give me the volumetric flow rate per unit depth? Okay. What was u in this case? U is the derivative of psi with respect to y. dy. Okay, well, what is the derivative of psi with respect to y? Just here's your function, your stream function right here. Is it equal to y v over h dy from 0 to h? So now we do that integral. Feels like we're going in circles. A little bit we are, but let's continue on. We'll have v over h times 1/2 y squared 0 to h. That's equal to 1/2 v over h squared 1/2 bh. And when you evaluate the lower limit, I was focusing on the upper limit, but the lower limit's 0. Guess what? The volumetric flow rate between two lines of the stream function at the top, the stream function at the bottom, is just psi at the top minus psi at the bottom. the stream function. So I know we're not making a big deal of it right now, but I'm trying to show you that's one of the deals is you can the lines of a constant stream function value, the flow between them, between those lines. This is a line here, top. That's a line in the bottom. The flow per unit depth is the difference in the stream function values. Now the linear momentum equation. We want to derive it. I thought the best way to do it is just sort of put it on the board and walk through it like I did the derivation for the continuity equation. What equation did I start with right here? Sum of the forces equal to, it's our control volume statement of linear momentum balance coming out of the previous chapter. It was like Reynolds transport theorem for linear momentum, okay? And so we have this MA on the right-hand side and the sum of the forces on the left-hand side. So we busted the sum of the forces first into body and then surface. The body force would be gravitational. That's the body force that we're dealing with all the time. You could put in there some magnetic body force, but it only makes it more complicated, and it's not in the standard Navier-Stokes equation. But gravity is. Surface force, you just have a surface force vector dotted n. So whatever force is acting on the fluid chunks at the surface, well, how could they be acting at the surface? Well, you introduce a stress tensor, sigma, and that stress tensor is it's a matrix. I've got the next slide that shows it to you, and we'll spend more time with it. But we want to turn this control surface integration into a control volume integration, don't we? How do we do that? Use Gauss's divergence theorem. This was already a control volume integration for the body force term. This is already a control volume integration for the traditional acceleration, and we used Gauss's divergence theorem for the advective acceleration term right here to turn that into a control volume. Notice that when you do the divergence of a rho v, v dot n, blah, 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 you pick up an outer vector product. It looks funny when you see it. It's just VV. I doubt they showed it to you in EA class. Maybe they did. It's in your book, though. Believe me, like a lot of other stuff is in your book. So you have the divergence of a VV, an outer product, not an inner product, of two vectors, which are the velocity fields. So now everything is on a control volume. You put everything together, you say it's an arbitrary control volume, the integrand has to be 0 at every point, and you derive Cauchy's equation. Okay? So I know that we switched sides. What was on the right now becomes on the left, but there it is. So this is our acceleration, advection of linear momentum, how gravity might affect it, and how forces, surface forces, can affect it. So what is that surface tension? It's a I'm sorry, not surface tension. A stress tensor, sigma. It's represented by a 3×3. There's 9 entities in it. Okay. And what I want to do is just describe each entity first. And what you do is you put a little cube in a x, y, z coordinate system, x, y, z coordinate system, and then you talk about the forces, perpendicular and shear forces, or perpendicular stresses and shear stresses on all of the faces of that cube. Because it's hard to see, we just show 3 that are lined in the positive x, the positive y, and the positive z direction. You also have it on the back sides. There's 6 faces to the cube. but here it's just showing 3. And so sigma xx is acting on the x face in the x direction. Sigma xy is acting on the x face in the y direction, and sigma xz is acting on the x face in the z direction. So the direction is seen, that's in the x, then in the y, and then in the z directions. But the first of the indices or the subscripts is what face it is, and it's described by the unit vector I. It's going in the direction x. Likewise, up here you have that. So what you do is you take that stress tensor. If I wanted to find the actual forces operating on something, you would multiply it by a vector. Maybe the vector, maybe I show it like this. 1i plus 0j plus 0k. If I did that, I would come back with a resultant force, which would be simply, maybe I should put 1 here times dA, everything times dA. I would have sigma xx times 1 dA. That would be in the I. And then you'd have sigma yx dA in the J. And you'd have sigma zx dA. I ran out of room in the K. Sorry about that. But you see what I did? That's how you would use this tensor. How many people have taken solids? How many people seen something like that in solids? No? Kind of. It's in your solids book, believe me. It's like in the fluids book as well. But you know what? 15 minutes and then you're done. It's like the polio vaccination. You just get the shot and then, right? Hopefully it's okay. That was, now let's say I have a face that was 0, 1. That's now the top surface. Let's say I do a face that's -1, 0, 0. That's the backside, right? Let's say I do a really weird face. It's -1, -1, -1, and so that's kind of a weird area, but it's not perpendicular to any axis. It's a combination of all, but that's how you would use it. Well, look, have to speed up here. Sorry about that. But you take that stress tensor and you bust it into the hydrostatic component, which is just all acting normal, and the viscous component, which are all shear. And then you study a little bit and say, I only want to deal with Newtonian fluids, because Newtonian fluids are simple compared to non-Newtonian, true? And so when you do that, a few steps gives you this form for the hydrostatic pressure as well as the viscous shear stress component of that stress tensor. Stick that, well, here's one way of describing it. One of the steps is that the viscous shear stress is proportional to the strain rate tensor through the viscosity, So you'll see that viscosity populating that viscous stress tensor. Anyway, the bottom line is there's a lot of algebra, which I don't have time to go through, and you're able to transform this component to this component. It's only good for Newtonian. This is general. This is Newtonian fluid. And also this component comes out. Okay? And then the outer vector product here, I'm showing you what it is. It's UU, UV, UW, blah, blah, blah. You work on that with some algebra and you turn that into the material derivative of the velocity vector. That accounts for the transient or the typical acceleration, how it changes with time, and a vective acceleration of the fluid through that point. And there it is. That's the Navier-Stokes equation. We can apply it. Let's solve one problem. Consider a steady, incompressible laminar flow of a Newtonian fluid in a narrow gap between two infinite parallel plates with an applied pressure gradient. The applied pressure gradient means over here at surface 1, it's at pressure P1, and over here it's at pressure P2. Typically, if the fluid's going that way, P1 is greater. Okay, that would be what they call a favorable pressure gradient. It's pushing it down the pipe, okay, or between the two flat plates. Also, this top plate is a moving plate. The bottom plate's fixed or stationary. It's not moving. So before, if you had no pressure gradient, the velocity profile looks like this. The top plate's moving, and there's no pressure gradient. Or if the top plate's not moving and there's a pressure gradient, the top plate and the bottom plate aren't moving, the velocity profile looks like this, doesn't it? It'll be maximum in the middle. Now, if you have the top plate moving plus a pressure gradient pushing it in the direction of the moving plate, you get a combination, and maybe the velocity profile looks like that. Can you see that where it bulges out a little bit from the triangular shape? Okay, well, you can predict that. You can predict the shape of that analytically. So calculate the velocity, u, that's u as a function of y. Try to get this shape in terms of a generic y. How far, y goes between 0 and h. V, that's the velocity of the top plate. H, the separation. Mu, oh, I forgot what mu was. Viscosity. And what's this? The pressure gradient. So, that seems like a tall order. What you do is you start with the continuity and the Navier-Stokes equation for steady laminar flow of an incompressible Newtonian fluid. What is this equation? Yeah, that's our del dot V equal to 0. It's our divergence, it's our continuity equation for incompressible steady flow, right? So that's it. And then this is the x component, the y component, and z component of our general Navier-Stokes. That's this equation in its glory, but I've written it out. All right. So now let's start going through this, striking the terms that are non-zero. How about the continuity equation? First of all, is there any v? Everywhere you see a v, it's 0. Everywhere you see a w, it's 0. So I see a v right here. That whole thing is 0. I see a w right there. That whole thing is 0. 0, 0, 0, 0. See that? How about the derivative of v with respect to x? It's not changing. 0. W, the derivative of w with respect to x. See, those terms are all 0. So we get to play a game of striking a lot. How about transient, this change with respect to time at steady state? All right, we're going to end that. We're going to have to stop striking some terms, but let's continue on. For the y component, this term is non-zero. Gravity is negligible. Let's take a look at this viscous term. U doesn't vary with x, but it does vary with y. So those are 0, but this is non-zero. And then these are all zeros. Okay. The pressure gradient with respect to y and z is 0. So what do we get out of this bottom equation? Let's say for the z, 0 is equal to 0. You don't do much with it, but it's satisfied. How about the y? 0 is equal to 0. You don't do much with it, but it's satisfied. Now we get this equation, which is that rho u partial u with respect to x. And now we can change that partial derivative into a ordinary derivative because, hold it, I'm back up. Does u change with x? No, it doesn't. U changes with y. It's fully developed. U doesn't change with x. It changes only with y. So that term's 0. So we get 0 is equal to negative dp dx plus mu second derivative of u with respect to y squared. When you've reached steady state, there's no longer any fluid acceleration. That's why that whole left-hand side is 0 on the x equation. All right. But we do have the pressure gradient and the viscosity. Okay. All right. What do we get out of this equation? Actually, that told us the continuity equation that the change in u with respect to x has to be equal to 0. So this is all of the continuity and the Navier-Stokes boils down to this equation. This is a constant. This is a property. This u I'm looking to solve as a function of y. It's a second order ODE. Separate and integrate. True? So if we separate and integrate, what do we get? I'm going to try and erase a little bit up here. You get that second derivative of u with respect to y squared is equal to 1 over mu dp dx. Okay, so we put the dy there, and you have the derivative of du dy, and so we integrate, so you have du dy is equal to the integral of this. You pick up 1 over mu dp dx times y plus some constant of integration. True? Separate and integrate again, you'll get u is equal to 1 over mu dp dx 1/2 y squared plus cy1 plus c2. Two constants of integration. I need two boundary conditions. The first boundary condition is for this location. U at 0 is equal to 0. How does that affect either C1 or C2? Well, try it out. 0 is equal to blah, blah, blah times 0 squared. So that's all goes. And then I'm left with Cy times C1 times 0. And then I'm left with C2. So you conclude that C2 is 0 from that boundary condition, the first boundary condition. Then the second boundary condition is U at H is equal to cap V. True? And so with the second boundary condition, we get U is equal to 1 over mu dp dx 1/2 h squared plus C1 h. This is now cap V. Can you see that I solved for C1? So C1 is equal to the minus 1 over h. Get rid of that. There. Makes sense? So now I have solved for it. We just have to simplify it. Let me try and tuck it in down here. That u as a function of y is equal to v over h Did I mess up the algebra? Okay, let's continue on. V over h times y, that's right, plus 1 over mu dp dx times, let me put the 1/2 out here, 1/2. We're going to have y squared minus h times y, like that. I think that's it. It can be simplified some more, but all I had to do is take that c and stick it back into there and write the equation for u. There you go. Are you impressed?